sir. We are about to start our class.
What?
We are about to start a class now.
I just want to check the computer real quick. Left a flash drive.
Okay, so it's 11 o'clock. Time to get started with our lecture for today. So you can turn off your computers. It's time to get started. So the first thing we're going to do is to collect the homework for today. So if you can please pass your homework to this side of the classroom. As you saw, there were only 10 problems in the homework. I was only requesting you to submit 5 of them, but I really encourage you to work on the other 5. That will help you prepare for the exam next week. And also, that will give you a better understanding of how to formulate problems, which is a very important part of this class. Here's the assignment sheet for today. So any questions about the homework? As you saw, there were 2 main parts. The first part of the homework was the graphical solution for linear programs with 2 variables. And the second part was modeling linear programming problems using just formulation. Okay, so we're going to start from there today. We're going to continue discussing how to formulate certain type of problems that you might find in your career. And there's two other problems that I want to discuss today. The first one is the project selection, and the second one is related to the oil industry. And I think some of you mentioned that has a specific interest on the oil industry, so I think that last problem that we're going to discuss today will capture your interest. Also, we're going to have a practice problem after we discuss these two, that you're going to have an opportunity to work in groups on that particular problem. Okay, so let's discuss this project selection problem. So what we have here is a company that is considering 5 different investment opportunities. The cash outflows and net present values in millions are given in the table. So I already know that you all took the engineering economic class, so when I talk about the net present value, I assume that you know that you are taking into account the interest rate and the time value of money. So we are considering 2 different times, time 0, which is right now, and time 1, which is a year from today. So we have different opportunities in terms of investment. We have 5 projects, and we have the net present value for those projects. Okay, so that's the information we have. The company has $40 million available for investment now at time 0, and it is estimated that a year from today we're going to have an extra $20 million for investment. So we have 40 right now and 20 in a year. The company may purchase any fraction of each investment. In this case, the cash outflow and net present value are adjusted. So for example, if we decide to purchase only 1/5 of investment number 3, that means that the cash outflow will be 1/5 of that investment, which will be $1 million. So it's going to be 1/5 of this $5 million. And the 1/5 share of investment 3 will give a net present value of 3.2, which is also a 1/5 of the 16 million. Okay, so the company wants to maximize the net present value that can be obtained by investing in any of these projects right now and in a year. Okay, so we want to formulate an LP that will achieve this goal, assuming that any funds left over at time 0 cannot be used at time 1. So right now, we have to use the money for right now, for the time 0. If we're not using that money, then we cannot take that money to the next year. So we have to use that $40 million at time 0 and the $20 million at time 1. Okay, so what will be the question to be answered? Again, this is the main part. If you are able to formulate this question, then you will have a better idea of how to formulate the problem. So we're talking about investments here. And we have 5 different types of investments, and we have 2 different time periods. So the question is, what fraction of investment to purchase? Okay, so again, we have 5 different types of investments. So we're going to use an index to identify each type of investment. So we're going to use I, and I1 will refer to kind of investment number 1. I2 will be investment number 2, and so on. So we're going to have a decision variable that is basically going to tell us what fraction of each project are we going to buy or invest. Okay? So that's our question, and this is the decision variable for that particular question. Okay? So now that we have our decision variable, what's next? What do we need to know? Or what do we need to formulate? Correct. Correct. So we need to formulate our objective function. And as the problem says, what we want to do is to maximize the net present value earned from the investments. Okay? So we know how much money we can make from each investment, right? And that's what we're going to use in our objective function. So we want to maximize the net present value that we're going to get from the investment we make to each project. Okay, so that's our objective function. And as you remember, the net present value for project 1 was 13, and so on. So after that, the next step is to formulate our constraints. And I'm putting the table one more time here because we're going to need this table for our constraints, to formulate our constraints. So in this case, we have 3 main constraints. The first one is we know that we cannot invest more than 40 million at time 0. And we also know that we cannot invest more than 20 million at time 1. So those are our first 2 constraints. We also know that we cannot purchase more than 100% of each investment. Okay, so our investment needs to be less than or equal to that 100%. So in order to formulate that first constraint, we know that we cannot invest more than 40 million at time 0, and we know the amount that we need to invest to each project if we want to buy that project at time 1, or at time 0, sorry. So we're going to add the total investment per project times our decision variable for that time 0, and we know that that amount that we're going to invest at time 0 needs to be less than or equal to the money that we have available, which is the 40 million. Okay, so if you end up only investing in project 1, the 100%, then you know that you're going to invest 11 million. All the other variables will be 0, and that 11 million is less than 40 million. So the constraint is going to be satisfied. But ideally, what we want to do is we want to find what is the best combination of the projects to invest at time 0, so we can use all the money that we have available and maximize our profit. So the second constraint is basically the same thing. At time 1, we know how much money we have to invest in each project, but we have a constraint that tells us that we only have 20 million after a year. So our investments are limited at time 1 for that $20 million availability. Okay, so these 2 constraints are very similar. The only difference are actually the money that you have available and the numbers that you're using for investment. And the last constraint is basically telling you that you can only purchase 100% of each investment. You cannot purchase more than 100%. Okay, so for each investment, X1 needs to be less than or equal to 100, and so on. Okay? So the formulation, as we explained again, this is our objective function. These are our constraints. Those are the two for the investments, and these are the ones that telling you that you can only purchase maximum of 100% of each investment. And you also have the bounds, so you know that your constraints for the variables needs to be greater or equal to 0. You don't want any negative values for your values. Any questions? We have one more problem to discuss, which is the blending and refining problem. And this problem is a little bit more complicated. It involves more thinking. So I recommend you to pay attention because it will involve several things. But let's discuss the problem. So first we have shale oil has a capacity of 1.5 million of barrels of crude oil per day. So that's the capacity. The final product from the refinery includes 3 types of unloaded gasoline with different octane numbers. So for regular is 87, premium is 89, and superior is 92. Okay? And the refining process encompasses three stages. The first stage is the distillation tower that produces feedstock of ON82 at a rate of 0.2 barrels per barrel of crude oil. So in order to produce a barrel of this feedstock, you will have to use 5 barrels of crude oil. That's what this is telling us. Okay? Then you have the cracker unit that produces gasoline stock ON98 by using a portion of the feedstock produced from the distillation tower at a rate of 0.5 barrels per barrel of feedstock. So you will need 2 barrels of the feedstock to produce a feedstock of 98. On the next slide, I'm going to present the diagram. It's going to be more clear. But just wanted to understand that in order to produce certain type of product, you're going to use the raw material that's coming from the stage before. And as you move on to the process, then you're going to be refining this process, and you're going to need more material from your previous process. Then the third stage is a blender unit that blends the gasoline stock from the cracker unit and the feedstock from the distillation tower. So here's the process. You start with the crude, and then you have a distillation station. So you will need 5 barrels of crude oil to create one type of ON feedstock. Okay, so 5 barrels of crude will produce 1 barrel of this feedstock. Now you will take that as an input, and you have another process here. It's called the cracker. So you will use 2 barrels of this product to create an ON98 type of product. Okay, so that's the ratio here, 2 to 1. And also you can take that input and take it to the blender. So the blender will take both the ON98 and the ON82 and will produce the different type of gasoline accordingly at a rate of 1 mole. So for those, you only need 1 barrel of each product to produce the certain type of gasoline. Okay? So this is the process. And as you can see, the diagram also shows you some of the decision variables that we're going to discuss next. So we're going to get back to this diagram in a few minutes. So let's look at the other constraints for the problem. So the company estimates that the net profit per barrel of the 3 types of gasoline is $6.70 and so on for each type of gasoline. The input capacity to the cracker units is only 200 barrels. And the demand limits of regular, premium, and super gasoline are 50,000, 30,000, and 40,000 barrels per day. So we want to develop a model to determine the optimal production schedule for the refinery. Okay? So what is the question to be answered? I'll give you some time to think about. So again,
How many barrels do
type of gasoline. Correct. That's the right question. So how many barrels per day to produce certain type of final product. Okay, so you want to know how much input do you need to produce the gasoline that you need at the end. So I'm going to use two indices, one for the input stream, barrels per day, and one called J, which is the blend of the final product. So this one is specifically for the gas. This is for the input. And my decision variables are going to contain both of the indices, Xij, which are the barrels per day of input stream I used to blend the final product type J. So I want to know how much input type 1 I need to produce certain type of gasoline, which is my type J gasoline. Okay, so we know the question that we need to answer. I'm using two indexes to define my decision variables. So you already have the decision variable. Now you need to formulate your objective function. But before we go to that point, let me talk a little bit more about the variables. So the variables can be defined in terms of two input streams, which are the blenders and which are the feedstock and the cracker stage, and also in terms of the three final products, which are the three types of gasoline. So as you saw on the previous slide, this is our decision variable. So we can use that definition to define the daily production of regular gasoline, daily production of premium gasoline, and daily production of super gasoline. So we can produce regular gasoline using two different types of inputs, the one that is coming from the feedstock and the one that is coming from the cracker stage. So we're considering those two variables to represent the daily production of the regular gasoline. And same thing for the premium. So the input coming from the feedstock and the cracker. So you need two decision variables representing that input, and the daily production will be represented by those two decision variables. And the same thing for the super gasoline. Okay, so in order to get the demand or daily production for each type of gasoline, you're going to be using two decision variables per product. Okay? And the reason why is because you're getting input from two different streams. So those two inputs needs to be represented in your decision variable. Okay? So you have your decision variables now. You can use the decision variables to formulate your objective function. So again, we want to maximize our total profit. So you know the profit that you can make for each type of product. So for the first regular gasoline, you will make 6.7, and you are multiplying that times your decision variables for the first product. And then you add the income for the second type of product and the income for the third type of product. Okay, so again, this is why we discuss the decision variables representing each product, because in your objective function, you'll be taking those decision variables, you will multiply that by the profit that you're going to be making, and then adding that, and that's the objective for this problem. Okay, so you want to maximize your profit, and your profit is represented by each type of product. Okay, so going back to the diagram, to explain, you have three different processes here. So the first thing we need to estimate is what is the daily output from this process. So your daily output is going to be this side of the figure. So we're going to have to represent this output according to the stages before in the process. Okay, so the daily output will be the daily production of the three types of gases. Okay, so you know that you can represent the regular with these two decision variables, the premium with these two decision variables, and the super with these two decision variables. So the final output is the summation of those decision variables, okay, which are here. Now, you want to know what is the daily feedstock to the blender. So here is our blender. So the input to that blender is represented by these decision variables, and these decision variables, which are the the process that is coming in here is the distillation, and the process that is coming here is the one from the cracker. So you know that our first index represents the process. So these decision variables first index are O1 because index number 1 represents the distillation process. Cracker process is represented by the first index 2. So these decision variables is the decisions or the summation of those variables with the first index. Okay, so the daily feedstock to the blender, which is here, is this part, the one that is coming from distillation. So this one is the one that's coming from distillation. And the daily cracker unit feed to the blender is the process, the output from the cracker to the blender, which is here. Okay, now the daily feedstock to the cracker. So the cracker is receiving an input from the distillation process, right? And we know that we require 2 units of the input from the distillation to create 1 for the cracker. So the input that is coming to daily feedstock to the cracker is multiplied times 2 because 2 units of the input will create 1 output for the cracker. So that's why we multiply that times 2. And the same applies to this process here, the distillation. So you will require 5 units of the input of the crude to generate 1 output for the distillation. So you multiply this times 5, which is this part here, and then this part times 5. Again, the ratio is 5 to 1 to represent the daily input to the crude for the distillation process. As you see, what we are doing is we're going from here to here because what we want to estimate at the end is how much input are we going to need for the crude in our process. Okay, so we started from the blender, then we moved back to the cracker, then we moved back to the distillation, and at the end we were able to estimate, based on our decision variables, how much input do we need for our process. Okay, so that's a daily crude oil used in the refinery. So we can use that to represent our first constraint. The daily crude oil supplies should not exceed these 1.5 million. So going back here, we estimated that input. So that summation has to be less than or equal to the availability of oil that you will have at the beginning of the day. Now, the cracker unit input capacity, again, we know that capacity is 200,000, and we know already the constraint that is going to be represented that input. So we can use the less than equal value here to constrain that input to the cracker. And then we also have the constraint for the daily demand of the regular should not exceed 50,000 barrels. So we now have to represent the demand of the regular, which is our 2 decision variables for index number 1 for J, and that has to be less than or equal to 50,000. Okay, so those are our first 3 constraints. We also have constraints for the demand of the premium. So again, it will be the same thing using the decision variables for the premium. It has to be less than or equal to our demand. And the same thing for the super. It has to be less than or equal to the demand of the super type of gasoline. Okay. We also have a constraint in terms of the octane number of the gasoline product, which is the weighted average of the octane numbers of the input stream using in the blending process. And that can be computed using this formula. So you can have the feedstock on times the feedstock barrels per day plus the cracker unit on times the cracker unit barrels per day divided by the total barrels a day of the regular gasoline. That will give you the average ON in your regular gasoline. So you need to satisfy that constraint. And for the octane number, for premium is at least 87. So when you use this formula to represent that constraint, you will have the 82, which is coming from here. You know that distillation will create a ON 82, and the cracker will represent an ON of 98. So you need to take into account those octane values to generate the premium octane. So you have the two processes represented in the denominator, the numerator, and then the denominator is just the summation of the total that you're going to produce for that type. And that has to be greater or equal to 87, which is the constraint for the regular type of gasoline. Okay? And we need to repeat the process for premium. Again, you have the same in the numerator. The only thing that changes is the decision variables used to represent the second type of gasoline. And in this case, we have a constraint that has to be greater or equal to 89, which is the ON for premium gasoline. And finally, we have the same constraint, but for the premium super gasoline, has to be 92. So finally, we are able to have our model. This is again a big model, but it is, I think it's a very good problem, especially if you're interested in the oil industry. This is the type of application that you're going to be looking at. Okay? So you need to take into account different things, especially if you're planning for the production and for the type of product that you want to produce. Okay? So this is our formulation for this problem. And again, you have to take into account the bounds. So you want to have your decision variables always being at least 0. You don't want to have negative numbers. Okay? So that's the last problem. This is the end of this particular lecture. So what we did was discuss the guidelines for the formulation. And we went through different examples, very applied examples for modeling problems in linear program, the diet problem, the production planning, scheduling problems, urban development problems, project selection, and blending and refining. Okay, so what we're going to do now is I have one more problem that I want you to work in groups, and so you can work in groups of 2. So please find a partner, and I'm going to pass this problem. This is a problem that is kind of related to the problem we just discussed. And again, the most important thing about operational research and in this class is you need to be able to formulate a problem. Once you get used to formulate problems, then the solution methods, I'm going to show you how to solve the problems by hand, but most of the time what you're going to be using is a computer to work together. So I'll give you 5 minutes to work in these problems, and then we're going to discuss the problem. And what we're going to do with this one, so this lab, if you get the right answer, I'll give you a point in the first exam. Okay, so this is to motivate you, try to get the solution. Try giving you a hint with the decision variable. You will need one more decision variable actually for this problem. Again, that the only way you can find out which decision variables you're going to need is by asking you the question, what do you need to do, what do you need to answer for this problem. Okay, so this is what I'm going to do. I'm going to start discussing the problem, but I'm going to leave one constraint out. And I'm going to ask you to finish the problem for next Thursday. Just complete that constraint. Actually, it will be that one of the hardest constraints for the problem. You will finish that constraint and you will submit that problem with that constraint next Thursday. Okay? So let's find out what will be the next or the other decision variable. So what is the other question that you need to answer here? In addition to the number of barrels of oil used to make product J, we have two types of oil. So this should be I. So we have 5,000 barrels of oil 1 and 10,000 barrels of oil 2. The company sells two products, gasoline and heating oil. Both products are produced by combining oil 1 and oil 2. The quality level of each oil is as follows. Oil 1 is 10, oil 2 is 5. Gasoline must have an average quality level of 8, heating of 6, and demand for each product must be created by advertising. Okay, so each dollar spent advertising gasoline creates 5 barrels of demand, and each spent on heating oil creates 10 barrels of demand. So we know the prices for selling the gasoline per barrel and the heating oil, and want to formulate the LP to help channel maximize the profit. Okay, so what is the other question I need to answer? You have to generate this demand, right? And you want to know how much you need to spend on advertising this type of gasoline. So that's the other question that you need to answer. So in order to do that, you need to define an additional decision variable. So we have the number of barrels of oil 1, oil I used to make product J, but we also need to, I'm going to use A for advertising. So we need another decision variable, which is essentially telling you the dollars spent advertising product J. Does that make sense? You don't know how much you're going to spend. That's something that you need to decide. And it's going to be decided based on the profit that you're going to make for each type of product, and also depending on how much oil you're going to use to produce each type of product. Okay? So we need to decide how much to spend on each type of advertising. So what will be the objective function? So the objective function. Do you have any information about profit here? Actually, the problem is telling you here, you want to maximize your profit. So that's your objective, right? So how much you're going to make by selling gasoline? 25 per barrel. And you also know how much you're going to make for selling heating oil, which is 20. So you're going to use that information. So you want to maximize your profit. So it's going to be, Z equals 25, and that's for product 1. So you have X11. This is the one that you sell by producing using oil type 1. And then you also have X21, which is also product 1, gasoline, but produced using type 2 oil. Plus the $20 for the heating oil using oil type 1 and using oil type 2. Are we done here? Are you having any additional profit or additional expenses in this problem? Yes. So there's a cost for advertising. So this will be, have to subtract that cost for the first product and also subtract the cost of the second product. So you have the profit sorry. So you have the profit and you have the expenses for the advertising. Now you need to formulate your constraints. So as I mentioned earlier, we're going to formulate some of them, but I'm going to leave you one or two for you to finish and submit. So the first constraint is the one related to the demand. So again, your demand is tied to the amount of money that you're going to spend in advertising. So you have a demand for product 1, which is represented by these two decision variables. And that has to be equal to the amount of money that you're going to spend here, which is 5 times the advertising. And the same thing for product number 2. We have X12 plus X22 equals 10A2. Okay, so you know that the demand is going to be equal to the amount of money you're going to put on advertising for each product. There's two other constraints. How about this one? You have a limitation in terms of the barrels that you have available for oil 1 and oil 2. So you need to establish that as a constraint. I'm going to leave you that one for you to work on the homework. So make a note, you need a constraint for the capacity that you have. And also you need a constraint for the quality. So you know the quality of oil 1 and oil 2. And you know that for gasoline you need at least 8. And for heating oil you need at least 6. So those are the constraints that you're going to have to finish on your own and submit by next Thursday. Is that clear?
Tuesday as in like the day of our test Thursday?
No, this Thursday.
Oh, this,
I'm
okay.
sorry, yeah,
Okay.
this Thursday, this week, okay? So, just finish the problem and submit it next time to your team. Okay, so, now we are gonna transition to a new topic. Which is, before we try to solve these problems using the computer, I want you to understand what the computer uses to solve these problems. And the algorithm that we're going to discuss in this lecture is called the simplex algorithm. And that's the algorithm that is coded behind these packages that are set to solve optimization problems, specifically for linear programs. So I want you to understand how the simplest algorithm works, and then I'm going to take you to solve the problems using a computer. Okay? So the material for this lecture is coming from your textbooks, the simplex method and sensitivity analysis from chapter 3. And also, if you want to read, before we go to the lectures, the objective for this lecture is I want you to use the simplest algorithm to solve linear programming models with more than 2 variables. So far in this class, I explained you how to solve these linear programs only for 2 variables. Do you remember what was the method you were using to solve them? Linear? Yes, correct. The graphical method. So if you have linear programs with 2 decision variables, it's very easy. You can use the graphical method, draw your constraints, and find the optimal solution. But if you have more than 2 variables, it's very hard to grab those constraints because you're going to be working on a 3D or 4D dimensional space. So the simplex method is going to help you solve problems that have more than 2 variables. And as recommended readings I have from your textbook, you can read sections 3.1, 0.2, and 0.3, which basically covers the material that we're going to be discussing in class. Okay? So, the introduction, so the agenda for today is the introduction to the simplex method, converting. I need to explain you how to convert an LP to a standard form because we're going to need that to use the algorithm. And also, I want you to get the feeling of how the graphical method help the development of the algebraic solution, and how is that used to implement the simplex algorithm. So we're going to show the preview of the simplex algorithm, and then actually go through the steps and work in the problem. Okay. So again, our idea or our goal is to solve these programs that have more than 2 variables. Okay, so first 3 weeks of this class, what we have done is we model LPs and we constructed these linear programs for different examples, and also we learn how to solve LP for 2 variables. But most real LPs have many variables, and a method is needed to solve the LPs with more than 2 variables. Okay, so we will study the simplest algorithm, which is used to solve the LP with thousands of constraints and variables. And most of the applications that you will see in real life would involve thousands of constraints and thousands of variables. So your linear algebra skills will now come into play. So remember lecture 2, the first thing we did in class was to go over linear algebra. You're going to be using that Gauss-Jordan method to solve problems using the simplex algorithm. Okay, so let's talk about how to convert LP to the standard form. So before the simplex algorithm can be used to solve an LP, the LP must be converted into a problem where the constraints are equations and all variables are non-negative. Okay, so When I say equations, I'm talking about instead of having a less than or greater than, you want the constraint to have an equal sign. Okay? So an LP in this form is said to be in standard form. Okay? So the steps in changing or converting an LP to a standard form are the following. If the constraint is less than or equal constraint, then we will convert it to an equal constraint by adding a slack variable. And I'm going to use SI to represent my slack variables. And the sign restriction SI less than or greater or equal to 0. So I'm going to add a new variable to those constraints. Those variables are represented by S. And I'm going to change that less than or equal sign to an equal sign. But I also have to constrain my slack variables to be greater or equal to 0. Now, if the constraint is greater or equal to a constraint, then we will convert it to an equal constraint by subtracting a excess variable and adding the sign restriction EI greater or equal to 0. Okay, so if we have a less than or equal constraint, we add a slack variable, and we add this sign restriction. If the constraint is greater or equal, then we subtract an excess variable. So I'm going to use an E to represent that excess variable. And we also add this constraint for the excess sign restriction. Okay? Now, if we have a variable that is unrestricted in sign, anyone remember what is an unrestricted variable? What is an unrestricted variable? So you have variables that are positive, you have variables that can assume values negative. An unrestricted variable is one variable that can assume positive or negative values. Okay? So if that is the case, we will replace that variable in both the objective functions and constraints by a new variable. And this variable is essentially using the difference of the same variable. So I'm using a comma and a double comma here to represent that difference, where both of them are going to be greater or equal to 0. And you will see how to use this in an example. Okay, but I'm just saying this now because this is something that can happen. You can have a problem that you would not limit the decision variable to be only positive. When those cases arise, you will have to make a modification to your problem to be able to solve it. And this is a modification. Okay? So, let's look at the first example. We have leather limited manufacturers, two types of leather belts, the deluxe model and the regular model. And each type requires 1 square yard of leather. So for the regular belt, we require 1 hour of skilled labor. For the deluxe belt, we require 2 hours of skilled labor. And we also have a constraint. In each week, we have 40 square yards of leather and 60 hours of skilled labor. And the regular belt contributes $3 profit, and each deluxe belt contributes $4. So we want to write an LP problem to maximize the profit. Okay, so decision variables, again, the number of each types that we want to produce. And the LP is essentially maximizing the profit. You will make $4 for each deluxe belt and $3 for each regular belt. So you want to maximize that profit. And you have constraint in terms of the leather. You only have 40 square foot of leather. And you also have a labor constraint. You only have 60 hours of skilled labor. And you know that the first belt requires 2 hours and the second one requires only 1. So this is our LP. Now the question is, if we want to change these two equalities, what to do? So we define each constraint a slack variable. as I mentioned. And why are we using a slack variable? Because this is a less than or equal sign. So, and a slack variable is the amount of the resource that will be unused in that particular constraint. So again, what we're trying to do is we're converting this LP so we can use it in our simplex method and find the solution. So that's the only way. You cannot use a less than or equal or greater or equal sign to apply the simplex method. You're going to have to use an equal sign for all your constraints. So using slack variables will allow you to create that equal sign for each constraint. Okay, so that's why we're doing this. So we're going to modify this, going from less than or equal. We're going to add some slack variables, and we're going to make those constraints equal sign. Okay, so let's change this to its standard form. So again, this is the same LP. And if you want to change this to in standard form, then we're going to add those slack variables. Okay, so for the first constraint, we're going to have x1 plus x2 plus the first slack variable for my first constraint, and this has to be equal to 40. So now we are changing our first constraint from a less than or equal to an equal sign constraint. We're going to do the same thing for the second constraint. So we have 2x1 plus x2 plus s2 is going to be equal to 60. And remember, those variables, those slack variables, has to be different for each constraint. So if you're using S1, you need to use a different slack variable for the second constraint. Those slack variables are different. Okay? So the last thing we're going to do is to put the non-negativity constraints for those variables. So x1, x2, s1, and s2 has to be greater than equal to 0. Okay, so we changed our LP to the standard form by adding those slacks and adding those non-negativity constraints. Now let's look at one example that we already discussed in class. This is a minimization problem. Remember the Dorian Alto, and she was trying to find out how to invest in commercials for wealthy people. So this is the same problem. I'm just using the same example. But in this case, this is a minimization problem, and the constraints have a greater or equal sign. So we want to transform this to a standard form. Are we using a slack variable for these constraints or not? Remember from the steps, well, we're going to add some variables, but these are not slack variables. I have a different name for them. Let me show you here. So if the constraint is greater or equal, what we're going to use is an excess variable. Okay? So greater than equal, excess variable. So let's work on this one. So we have a minimization problem. So minimize z equals 50x1 plus 100 x2 subject to 7x1 plus 2x2 2x1 plus 12x2, and we have E1 and we have E2 equals to 28 equals 24 are we going to add or subtract these variables? Right. So we subtract these excess variables. And we also have the constraints for the non-negativity. So we have x1, x2, e1, e2 greater or equal to 0. Questions? Okay, so now you're going to work on the next one. We have a maximization problem. We have less than or equal constraints, and also a constraint with a greater or equal sign. Anyone brave enough to change that to a standard form using the board? Bonus point for the exam. One bonus point if you do it right.
Is it just gonna, well, I mean, I'll do it, but I just wanna make sure before I go there. Is it, a slack? Is it left-handed?
You have both actually. You have slacks and excess. You just go, right?
Okay.
Yeah. Okay. So the first thing that I wanted to see is, you can stay there.
Oh.
Yeah. What we're trying to do here is to change this to equal sign constraints, right? So, yeah, that would be the first thing that you will have to change.
Oh.
Very good. The other thing I want you to see is that we're going to use only one slack variable per constraint.
Oh, so would you rewrite it then?
You see one slack variable per constraint, and it will be different to the other constraints. So if you use S1 on the first constraint, S2, that would be S3, correct? $6,000. And for that one, same thing applies. You only need one excess variable. It is an equal sign. You can get what you need. One, X2, E1, X3. Yeah, that's correct. Thank you. Any questions? Okay, very good. So again, remember that you need only one slack or excess variable per constraint. And that what we're trying to do here is to change this from standard form, from the original form to the standard form, which is using the equal sign for all our constraints. So let me write here, this is max z equals 20x1 plus 15x2 subject to x1 plus x1 equal 800, x2 plus s2 equals 800. Then you have 50x1 plus 35x2 plus s3 equals 6,000. And then you have 20x1 plus 15x2 minus e1 equals 2,000. And then you have x1, x2, s1, s2, s3, and e1 greater or equal to 0. Okay? Any questions? Okay, so you saw how to change from less than or equal, greater than equal, and the combination of the two. Now, I have another example, and this example is to show you a case where you have an unrestricted decision variable, unrestricted sign. So here we have a baker that has some product here, 30 ounces of flour, 5 packages of beef, and to bake a loaf of bread, you require 5 ounces of flour and 1 package of beef. Each loaf of bread can be sold for 30 cents, and here's where the problem gets interesting. So he can purchase additional flour at 4 cents, but he can also sell the leftover flour at the same price. So depending on the decision that he made or the program made, you will have a value positive or value negative for the decision that you're going to make in terms of the flour. If you decide to purchase more, that will affect your profit. If you decide to keep it and produce more bread, then that will affect your profit in a different way. Okay, so I want you to formulate the LP to help the baker maximize the profit. So the decision variables, number of loaves of bread baked, and I'm going to have a second decision variable, that is the number of ounces by which the flour supply is increased by cash transaction. So X2 is the one that is going to tell me if I'm going to sell the remaining or if I'm going to buy more flour. So if I formulate this problem, I want to maximize my profit. So my profit is 30, which is the amount that I'm making by selling each loaf of bread. And also I have a minus here represented x2, which is the variable that is going to tell me if I'm selling or keeping to produce more bread, the flour. And also I have a constraint for the is available. So as you can see, x1 is greater than 0, but x2 is unrestricted in sign because you don't know what the program solution is going to tell you. If you're going to sell or if you're going to keep it or buy more to produce more bread. So as a note, if x2 is greater than 0, then that means that x2 ounces of flour were purchased, and this is a typo. If x2 is less than 0, that means that these ounces of flour were sold, and if it is equal to 0, no flour was bought or sold. So as you can see, x2 will be unrestricted in sign because it can assume any values, negative or positive. Okay, so that's the formulation. Now, the problem is how to change this problem to standard form, because we have a variable that is unrestricted in sign. Okay, so that makes things different. And this is how I identify an unrestricted sign variable, URS. Okay, so I'm going to use this example to change this to a standard form. So let me go back to slide 7. Let's see if I can do that. Okay, so in here, this is step 3, remember? If the variable is unrestricted in sign or free, replace that variable in both the objective function and the constraint by this new variable. Okay? Where both of them are going to be greater or equal to 0. So that's what we're going to do here. So let's start with the objective function. Maximize z equals 30x1 minus, so now x2 is going to be equal to x2 prime minus x2 double prime. Okay, so using this and using the substitution, we have 4x2 prime plus 4x2 double prime. And that's our new objective function. And this is going to be subject to 5x1 minus x2 prime plus x2 double prime plus s1 equal to 30, and x1 plus s2 equal to 5. So x1, x2 prime, x2 double prime, s1, and s2 are greater or equal to 0. Okay, so again, this is the case in which you have an unrestricted variable. So you have to make that substitution. x2 now becomes x2 prime minus x2 double prime. And this is how you change it to a standard form. So later in the class, I will show you how that variable affects the solution. But at the end, when you get the solution for the problem, then you're going to have to go back to x2, substitute the values of x2 prime and x2 double prime, and get the value for x2. Okay? So, let me see what else do I have here. So I think this will be a good time to stop because I don't want to transition to the new topic. Any questions? Okay, so for next class, remember to work on the problem that we started here. We're gonna complete the simplex algorithm on Thursday, and that will be the last topic for our exam next week. Okay, so I encourage you to start looking at the material. Stop by the office if you have any questions, or send me an email. I'm going to post the solutions for the second homework today, so if you want to take a look at the solutions. And I have your first homework here graded, so you can collect your homework before you go. If you don't have any questions, I'll see you on Thursday.